has to give another talk at an event in Berlin today. So she can't be here, but I do my best to also do the talk without her. So, what are we going to do? So we're going to basically go through a 25-minute crash course on everything there is to know about pseudonymization and anonymization. And that looks, of course, a bit challenging, yeah, and it is. But the first thing that I want to show you is that all the material that I'm going to show is available online. So it's based on a training that we did this summer at the EuroPython. You can see the GitHub URL here, and all the techniques and the methods that I'm going to talk about, you can find the documentation, the source code, and the data there online and can go through that yourself. So, first thing that's important is to distinguish data security from IT security. Because data security is not about choosing a safe password for your database, but it's instead about transforming or changing your data to making it secure to work with it or share it with other people. And that's very important because today a lot of the data breaches that happen, like recently with Google Plus or with Facebook, don't happen because companies get hacked, but they happen because companies publish data that they think is harmless, but it turns out to be actually sensitive and dangerous for people actually. And what's the worst thing that can happen, you might ask? Well, I don't know if you saw that, but kind of the worst thing is that you have to wear a nice suit and then testify in front of Congress and explain why you handed over data to a foreign government and help them to rig your election, so to say. And of course, we don't want to do that. But there are also less extreme values, of course, to think about data security. And some of them are ethical. I mean, privacy is a human right even. So you should ensure that the users can maintain their privacy. And we as data scientists should, of course, act professionally when dealing with sensitive or problematic data. Now, you can also ask a lawyer if you have a problem with data security. It's likely that then afterwards you have a lot of problems with data security because he will tell you about all of these regulations, and there are quite a couple of them that you need to follow. GDPR, the General Data Protection Regulation here in Europe, is only one. There are other ones like HIPAA, which applies to medical data in the US, or PCI, which applies to banking or credit card data. And every year, or almost every year, there are new regulations being created because governments also see that protecting data and securing it is important, so they really enforce a given security standard in companies, which is a good thing in the end. And finally, there are also business reasons, of course, because leaking sensitive data, as we have seen in the past, can be a disaster for your company. You can get lawsuits, you can get a reputation damage. But on the positive side, if you care about data security and privacy, it can be also a strong selling argument. Like Apple, for example, has this as its primary advantage, so to say, or like a USP in comparison to other smartphone manufacturers. So data security is important, and there are many ways to secure your data. Some of the things that I show here, like homomorphic encryption or other techniques, are still a bit academic in the sense that they don't work very well in practice yet. Other things like federated learning work quite well. But in this talk, we're only going to talk about two things. That's pseudonymization on one hand and anonymization of data on the other hand. And of course, the first thing that you need to know is the difference between the two. And that's most easy to explain by looking at this table here. So that's just a made-up example of some personal data. So we have a name, an age, a gender, a zip code, and some attributes that might be sensitive, like information about a health condition or something. And on the left side, you see the raw data, so the original data here. On the middle, you see the pseudonymized data. And on the right side, you see the anonymized data. And what pseudonymization basically does is that it prevents someone who looks at the data to single out a given person based on a direct identifier, like a name. So if I would, for example, look in the middle here and I want to know, okay, what's the attribute X value of Della Rosman? I can't find that because instead of her name, there's only a number, a pseudonym that we replaced her original name with. And that in that sense makes the data a bit more secure than the raw data. But there are still some ways in which an adversary could know something about Ella, because I could also say, okay, I know Ella is 38 years old. She's a woman. She lives in the zip code 10742. And then I can go through this pseudonymized data. And often, if I have many of these attributes, I can chain them together to a so-called quasi-identifier. And then there will be only one row in the data set that really matches this person. So these attributes together act like a fingerprint that can uniquely identify someone in this data set. And to avoid that, I really need to use anonymization. And that's what's shown on the right side. In this case, the anonymization was done by grouping the data together. And it works basically by making it impossible to single out a single person in this data set. So now if I would say, okay, I know still that she's 38 years old, she's female, she has in this zip code 07, etc., etc. So she must be in the first row of this data set. But I can't say with certainty then what is her attribute X, because in this row, there are two people, not only one, and two different values of this attribute. So in that sense, I protected the privacy of Ella here with this very simple technique. And we're going to see later how we can do that in practice with large data sets as well. So, but let's have first a look at pseudonymization. By the way, there's a seahorse here in the photo, but I don't know if you can see it because it's pretty well pseudonymized as well. So pseudonymization is pretty simple. Many of you might have encountered that in practice already. There are basically two methods that you can use. One method is so-called mapping-based approach, where you have a table or a database that would help you to look up a pseudonym for an original value or create a new pseudonym if none exists already, and then replace the original value with that. And this also helps you then to go back from a pseudonymous value to the original value by looking it up in the database. So a very easy, straightforward way. Today, a lot of companies also use cryptography-based methods like hashing, where instead of having a table and some generation function in there for generating the pseudonyms, you use a cryptographic method to also produce a unique value for a given input value and then map that to a pseudonym. And typically you need a combination of the two approaches, because even for the cryptography-based one, you will need a table where you store your pseudonyms if you want to go back to the original value, since a hashing function normally cannot be inverted without knowing that original value. So in that sense, these techniques, they're quite simple, but they're not very interesting for data science because they destroy most of the utility of the data. If you have a number or anything else and you hash that, you get out a hash value and you can just make comparisons based on identity. So you can know if two values are equal, but you can't say anything else about these values. So from a machine learning or data science perspective, the data is almost useless. And that's why we started to think about other ways for pseudonymizing or protecting data that use so-called format or structure preserving techniques. And again, the principle is quite simple. You can imagine you have some input value from a given domain, in this case an IP address, and you want to pseudonymize to another address that protects the identity of the original value. And basically what we do here is that we first transform the input value to a binary representation, so basically a stream of bits. Then we pass this binary representation to a cryptographic function that does something to that. And produces in the end another binary representation of the same length, which we then map back to the original data domain, in this case an IP address. And there are actually techniques that allow us to do that in such a way that the mapping is unique, so we can't have any collisions, it's reversible, and it can optionally also preserve some of the input structure of the data. Now that sounds a bit abstract. We actually developed this last year in a project where we handled so-called network flow data for a customer. And network flow data is basically meta information about connections on computers on a network. So it would say, okay, computer A with IP address X has communicated with computer B with IP address Y. And you can, of course, use the data for interesting things like threat analysis or anomaly detection. But as you might know, the GDPR says that IP addresses are also personal data, so you can't just publish them or use them in your research. And hence we needed a way to protect them. And all the methods that we looked at were not suitable because we really had quite strong demands here in terms of both speed, because we saw many millions of flow values per minute that we needed to pseudonymize or protect. We needed to do this decentrally because we had many different network sensors from which we wanted to collect data without coordinating that centrally. We wanted it to be reversible as well in order to go back to the original values if you needed to. And we wanted this to not rely on any databases or tables because the speed and the decentralization made that very difficult to realize. And we went through the literature, tried to find a method that would do that, but couldn't find anything. So we developed one ourselves, and currently this is closed source still, but we hope that beginning of 2019 we can publish a paper about that and also release that as an open source version. And now what we have for now is an API that is also free to use. Here I have like an example that shows how we can use that API for a so-called packet capture file that contains these net flows together with the data that they carry. And so if we run that, we can see that we have then one pcap file here in this directory. We open that with Wireshark, and you can see there are a lot of IP addresses, some local, some global addresses in there, and those we want to protect. So what we do is we call here a local version of our API with our very secure password, test1234, and then pseudonymize this data. We get like an output file. We can open that again with Wireshark. And as you can see, the resulting data looks very similar to the input data, but all the IP addresses have been replaced. And in such a way that the subnets, so for example, the 192 subnet gets always mapped to the same address. So this data is still very nice for analysis, but it's very difficult for an adversary or someone else to figure out what the original IP address was, because this is really based on a sound standard cryptographic method. And this is nice, so this works quite well. It's quite restricted though as well because it's only for IP addresses. And so what we did next is we wondered, okay, can we maybe apply that to machine learning as well? And we had one example data set that we looked at. It's a so-called wine data set, which contains chemical features from different wine samples. So a few thousand wine samples from, I think, 4 different producers. And the idea here was that like the different chemicals would indicate where the wine comes from, and we can use a machine learning model to predict which producer produced a given wine sample. And this is a standard data set in scikit-learn, so we loaded that. The features are numeric, so they are floating point values that we can represent as integers. On the right side, I show you one example feature, which goes here from 1,100 to 1,500. And what we did there is we just applied the same structure-preserving method to this data. So we mapped the input integers to new values in the same domain. And this is shown on the right. So we can see on the left side the original value there. And the connecting line shows you to which value on the right side this input value has been mapped to. And this looks a bit garbled, but you can maybe also see that on average, due to the structure preserving property of this method, the distances between the data points are more or less preserved. So data points that were closed before are mostly also closed in the pseudonymized data. And this is great for machine learning because most of the machine learning methods, they don't care so much about the order of the data points, except maybe if you're doing linear regression, but they care more about the structure. And the two methods that we tested on both the original and the raw data, actually a decision tree and a support vector machine, were both able to work with this pseudonymized or protected data with only a little loss in accuracy. So in this example, which we also have online in our workshop, you can see that it's only like a 3 to 5% drop of the accuracy when working with the pseudonymized or protected data instead of the original one. And that's nice because it shows that you can encrypt your data in this format preserving way and still kind of work with it. So, of course, this is still very basic. We're working now on to also offer that for different data types, but it offers already a very good level of security because you can, for example, also rotate the encryption keys, which we show here. And if you do that, you would also produce a completely different new set of mappings. And in that sense, it's, if you do that often enough, quite secure against at least simple statistical attacks. You can, of course, also turn off the structure preservation. Then you get this result here, which looks more like a modern art installation. When we ran this against our machine learning methods here, they actually had a lot of problem because you can imagine there the structure gets completely lost of the output data. So neither the support vector machine nor the decision tree was able to extract anything meaningful here. So as a summary for this pseudonymization section, we can say that you can, if possible, you should always try to pseudonymize your sensitive data, either with like one of these traditional methods or with a structure preserving method, because that also allows you, for example, to work much more easily with the data internally. GDPR, for example, makes it possible even to work with pseudonymized data, for example, when you don't have the explicit consent of your users. So if you have some user data and they don't give you consent, for example, to do the machine learning on it, then you can relax this requirement if you not work with the original data, but use the pseudonymized data as well. So in that sense, using this technique can give you some flexibility and make it easier to work with data that you couldn't use or analyze before. And the format preserving methods are still a bit limited, so we're working on extending that, and we also hope to publish some of that next year. So let's look at anonymization. Again, this here shows very nicely how anonymization should work, because a good anonymization method should allow you to see the big picture, but at the same time make it very difficult to single out a given individual. And one of the most used pseudo-anonymization techniques to date is still the so-called k-anonymity method, which has a pretty simple idea. So again, we have like an example data set that you see on the left. We have a few attributes about the age, the gender, and the height of a person, which we call the quasi-identifiers, and we regard them as non-sensitive. So we don't think it's a problem if some of this information would leak. On the other hand, we have also one sensitive attribute, for example, again about a health condition here, that we want to avoid leaking to a third party. And k-anonymity does that by saying, okay, if I want to prevent a person from singling out a single row in my database, I can just group some of the rows together and just report aggregate values. And then even if a person as before would know, okay, the person I'm looking for is between 18 and 35 years old, male, and like 1.75 meters tall, he or she could still only narrow it, the possible values down to these two here, and wouldn't know, for example, if the person would have a positive or a negative attribute. In that sense, grouping the data together in this way protects the privacy of the individuals in this database. Again, we have an example data set here, in this case income data, which contains some quasi-identifiers here, age, number of years of education, etc., as well as the income as a binary attribute. So basically it says if a person earns less or more than $50,000 here. And yeah, if you think that's not a sensitive information, then you should try to ask some Germans about their income, and you will see that, yeah, it's definitely very sensitive, so we have to keep that private. And k-anonymity, again, is not a method, but mostly a property of a data set, so we still need some way to produce a k-anonymous data set. And a very effective, very simple method is the so-called Mondrian Algorithm. The idea here is very simple again. It starts out with the whole data set in a single group, which is then in most cases k-anonymous because you have a lot of data points in there. And then the algorithm tries to subdivide this group into smaller groups until no more subdivisions are possible. So in that sense, it's a top-down method that starts with one group and then makes smaller and smaller groups until the k-anonymous criterion can no longer be fulfilled. And an example is shown on the right here. So we have a data set with two features, feature A and feature B. You can see the different data points in there. And now the Mondrian algorithm would say, okay, I can partition this data set vertically here. So this gives me these two new partitions. Then I can do that again horizontally. And I can still partition that further. So I can do it vertically again. In the end, I have this nice picture here with these 4 k-anonymous, in this case, 2 anonymous groups. And it is called Mondrian because, as you might see, it looks a lot like the paintings by Piet Mondrian. If you apply this to our example data set, the result looks like this. So you can see here, we do this for 2 features, age and years of education. And if we look at the resulting data, you can see that here in these 2 tables for like the left extreme value and the right extreme values. And you see that for each combination of the quasi-identifiers and each value of the income, we have either 1 or 2 rows in this database. And the rows corresponding to one group should always add up to a count that is larger than 3 in this case. You can see that it's always given, so in that sense this dataset is k-anonymous, but you might notice a problem here because some of the groups they have only a single value of the sensitive attribute. So for example, in the first group there, you can see that the income of all the people is less than 50K. So if now someone can single out this row on the table and knows, okay, the person he is looking for is in this group, then he also knows immediately that that person has less than 50,000K income because all of the people in the group have that. So in that sense, we can't protect the privacy like that. And that's of course bad. And we can fix that by so-called L-diversity scheme, which is a modified K-anonymity algorithm that uses another criteria. Basically, it says for each group that you create, you need to create at least L different values of the sensitive attribute. In our case, that would be 2. And you can see now the groups are a bit larger. And if you now look at the rows again here of the table, we can see that for each group, we have now 2 different values of the sensitive attribute. And this is much better than before, but it's still a problem because you can see that the distribution is quite extreme. So in this group, for example, there's only one token person with an income larger 50K and everyone else has an income smaller 50K. So it's still not very good privacy, I would say. And again, we can fix that by so-called T-closeness, which ensures that the distribution of the sensitive attributes now in each group is close to the distribution of these values in the entire data set. And again, we have different methods to enforce that. We have that in the example code if you want to have a look. And if you look at the result now, it looks much better because all the groups are much nicer distributed and we couldn't easily single out a given value here for a person, or at least not as easily as before. And if you look at a comparison of all of these 3 together, you can see that the more privacy, the more secure we make the data here, the more we have to pay in terms of aggregation. So we lose the more utility, the more security we create in general. Especially for the T-close values, you can see that here on the left and here on the right, we have very large groups now where we had very small groups before. So to summarize, this method works very well, but it only works mostly for low-dimensional data sets. So if we have a small number of quasi-identifier attributes and a small number of sensitive attributes. If that's given, you can do that. The grouping is actually an NP-hard problem, but there are good methods available for doing that. This Mondrian works quite well, for example, but it becomes, as I said, intractable if you have a large number of quasi-identifiers or sensitive attributes. So the last thing I wanted to quickly talk about is then differential privacy, which is the cool kid on the block, so to say, for thinking about anonymization algorithm. Again, it's not a method, but it's more a way of thinking about probabilistic anonymization methods in the sense that it tells you how good or how bad, so to say, a given method is. And the nice thing about this scheme is that it doesn't require any threat modeling or any definition of sensitive attributes. So there's not much we can do wrong here. In that sense, it's more like a cryptographic standard security model than like a very restricted domain model for privacy modeling. And it sounds very abstract again. So here's another example. It's called Randomize Response. This existed actually way before differential privacy. And it works like this. Again, we can imagine we want to ask a person about the income. And instead of asking directly, we say, okay, flip a coin first. And if the coin comes up head, then report the true value. But if the coin comes up tails, then toss another coin. And if that coin comes up heads, then report an income larger than 50K. If it comes up tails, then report an income smaller than 50K. So that means a percentage of our users that we can choose here with a probability P will actually lie to us and report a completely false value. And if we do that with our data, you can see here that you have the original data and the differentially private or randomized response data in blue and in red, respectively. And where the two coincide, you can see this here in magenta. And now if you calculate the probability from this randomized data, given the different values for P, this is shown here. So if we set P to 0, that means basically all people report the true value. We get, of course, our original value back. So that's nothing surprising. If we set P to 1, we get only completely randomized data. And this stands here with a probability 50%. So this is completely useless in a sense because it doesn't contain any of the original data. So in practice, we want to tune this value somewhere between here and here. And of course, if we would just use this value that we get there, we wouldn't get the true value. But since we know the model that generated these data points, we can calculate back from the probability dp that we measure here to the original probability of the given income distribution. That's a pretty simple formula based on the Bernoulli distribution. We can generate an estimator here, which I show. So you have these different distributions for, again, the p-values between 0.0 and 0.8. And as you can see, you can always get like a pretty good estimate, but as you increase the p-value, the variance of this estimate also gets broader, as you would expect, because we're putting more and more fake data into our real one. And you can see that here, what is kind of amazing about this method is that even if you set the p-value to 80%, so 80% of the people are actually reporting completely false data or random data to us, we can still, with a few thousand data points, get a very good estimate of this income probability here. And that's actually what Apple is doing, and they can turn that p value even farther because they have, of course, billions of devices, and it's, I think, one of the only systems where you can say you can put a lot of garbage in on one side, and on the other side you get a very nice result out if you have enough data. So summarizing, differential privacy is also a very good method to ensure the security or the privacy of data that you capture. This method here I showed you is working for single data points, but actually differential privacy also works on aggregate queries. So for example, if you're calculating means or other values, and it works even better because if you have more data, you need to inject less noise per data point usually. So, and again, there are different methods available to that, and if possible, you should try to apply that to your data. So to summarize, I hope I could show that data security is not magic. And I want to say, if you're working with data internally, you should strongly consider to use pseudonymization whenever possible. If you want to share data with third parties, you should consider doing an anonymization first. And again, if you want to learn more about any of the techniques I showed here, all of the code and the documentation is available in our GitHub data. And if you have any questions, feel free to send me an email, or I think we have maybe time for one or two now. Thanks.
So nice talk. I wondered if it was not enough to pseudo-anonymize the data and then throw away the relationship.
Yeah, so you mean if you apply this structure preserving pseudonymization and then just throw away the key?
Yeah, because then you're not one join away of ruining someone's day, but you can still, or you seemingly can still work with the data.
Yeah. So I didn't call this data anonymized for a reason, because for example, even the IP data, when you randomly reassign all of the IPs, it's still possible to learn something about that about the original values if you have enough context information. For example, if you know like some IP address correspondences, you can think about the statistics, and you know, for example, this host here sends a lot of data, and so you could figure out the relationships, and that's why it's not anonymized data. So anonymized data is really only considered anonymized if you can take all of the context information in the world and look at the data, and you still wouldn't be able to figure much about it out about it anyway. So that's in a sense a much stricter definition than pseudonymization. Yeah. So this data here would be pseudonymized in the sense that you couldn't directly see a relationship, but it's not anonymized because you can still, with enough context information, reproduce some information. Yeah. Does that make sense? Okay.
So pseudonymized IP data again. Does it also work for IPv6, your current implementation?
Yes, I don't know if you could see that, but we have a few IPv6 addresses in there. I mean, it's pretty simple because it's just a longer binary string in that case.
Okay, unless you take into account different treatment of subnetting and network masks and stuff like that.
The network masks we don't pseudonymize, for example. So if you have like a /24 or so, I mean, that's not, in our threat model, not sensitive information in that sense.
Okay.
But we could do it, of course, yeah.
And the second one, there was an ARP package, and it looked like you also pseudonymize the content of the package?
Yeah, exactly. For this ARP package, we do that already. For other contents, we don't have handlers for everything. But for the simple things where we know that there's an IP address inside, we also do that, of course. We also have support for MAC address pseudonymization, by the way. So
cool. Nice. Yeah. Thank you.
Mm-hmm. And yeah, as I said, we hope to publish that as open source next year. So we're still waiting for the go from our customer there. Yeah.
Have you tried the structure preserving methods also on, for example, image data?
Yeah, we thought about that, but for high-dimensional data, you kind of need a different strategy because, like, pseudonymizing each individual data point, for example, in an image or also in a time series, wouldn't produce anything that's very secure because it's like you need something that takes into account like the neighborhood or like at least the history of points, for example. And that's what we're working on right now. So, but it's a much more difficult problem, I would say, than this one here. So high-dimensional data is really quite unique in the sense that it's very extremely difficult to anonymize.
Okay, thanks. Okay, one last question.
Thank you for your talk. You demonstrated really clearly that the larger your data set, the less you have to do to it in order to anonymize your data, and that. But that begs the question: when can you start looking at your data, and how long do you keep unanonymized, unpseudonymized data before you perform the switch?
Yeah, I mean, in principle, you can even look at individual data points if you perform, for example, something like this randomized response scheme. There even a single point is secure because if you set your parameter to 80%, someone could only know, okay, with 20% probability, maybe the person reported this or this, but it doesn't give much information. So in that sense, even a single data point is already secure, but it's not very useful because it contains a lot of noise. And that's why I said like differential privacy works best if you can have a store of like raw data and then you make an aggregate query over that data and you anonymize the resulting query instead of the original data, because then you need to add much less noise per data point and you can get a much better result even. But of course, this is a different threat model because it forces you to keep the original data somewhere accessible. And this nice thing about the randomized response scheme is that you don't have this original data anywhere. Yeah. And for the other things, it depends a bit. K-anonymity works good if you have a large data set, but it depends again on the distribution of the individual data points, especially at the edges, So, yeah. Okay.
Okay, thank you, Andreas.
Sure. Thanks.